All right, so I'm going to just pick up where I left off. I want to talk about some other properties. And the one I want to talk about now are more information theoretic quantities, such as entropy and support size. So I mentioned already this example, so I'm going to skip that slide. And I want to talk about approximating the entropy. And I think we kind of have two ideas of what we mean by approximate in general. Usually we talk either about multiplicative approximations or we talk about additive approximations. And the complexity of these problems is very different. So let me first talk about multiplicative approximation because kind of I'm optimistic and the results here are better. So happier. Okay, so in general, you can't really get it. I mean, for kind of dumb reasons, you can't really multiplicatively approximate the entropy. And the reason is, and this is sort of clear, you can't really distinguish a distribution that's got almost zero entropy from zero entropy, right? You don't know if all the probability, let's say you take t samples. You have an algorithm that takes t samples, okay? And now you have a probability distribution that has a zero entropy, or you have a probability distribution that has, that there's one element that has probability 1 over, say, t squared. So you're really unlikely to see it. But it's not zero entropy. Okay, so a multiplicative approximation of entropy is supposed to say non-zero on that one, but it won't because it won't see it. Okay, so that's kind of a stupid reason why you can't get a multiplicative approximation of entropy. So you could do one of two things. You could say, okay, I want to get a multiplicative approximation of entropy as long as the entropy is at least a certain, say, constant. Or I could say I want a multiplicative plus additive approximation of the entropy. Okay, so you get multiplicative error and additive error. So that's, you can handle it in any number of ways, and the results allow you to shift between one and the other. So let's assume the entropy is slightly bigger. Let's say I want to gamma multiplicatively approximate the entropy. Gamma, think of as something bigger than 1. It can be 1 plus epsilon. It can be 2. So let's think about it being 2 for a second, okay? So we want to 2 approximate the entropy. And let's assume the entropy is at least 4 over epsilon. Okay, so I want what is epsilon? Epsilon is just some arbitrary small constant in this case, okay? So don't worry about epsilon. So it's something somewhat bigger than 4. This epsilon goes up here in this, it's hidden here in the exponent. So it's some constant. So it's some yucky thing that I'm trying not to show you because you're going to look at that and say, what's that? Okay, so let's just say the entropy is bigger than some constant, maybe bigger than 4. All right, and then we want to gamma multiplicatively approximate the entropy, and it turns out that 2 approximating the entropy only needs n to the 1/4 samples. Okay, so it's a lot less. Okay, it's not quite n to the 1/4 because there's some yucky thing here that I skipped. It's little o of 1, okay? But it's almost n to the 1/4 samples to 2 approximate the entropy. If you want to 4 approximate the entropy, it's n to the 1/16, okay? If you went to 1 plus epsilon approximate the entropy, it's n to the 1 over 1 plus epsilon squared, so it's a little less good. All right. Okay, so not only, and this is actually tight, we know that it requires n to the 1 over gamma squared. That is a Paul Valiant, 2008. And you can actually get better bounds when the support size is small, and you can, all sorts of things. Now, it's similar for estimating the support size of a, you can get similar bounds for estimating the support size of a distribution. Okay, so I'll leave it at that. But what if you wanted an additive approximation to the entropy? Okay, so now if you want an additive approximation, and that's usually when people talk about approximating the entropy, this is actually what they're talking about. It's not clear to me if that's what they need or that's just what they're used to looking for. So that's not a question I can answer because I don't know how they use it. But these people, they tend to talk about additive. That needs theta of n over log n samples, and this is due to, okay, so there was a sublinear result due to Raskhodnikova et al., but then Greg and Paul Valiant showed that the tight result of n over log n for this problem. Okay, and it's a really beautiful paper again. It's the same papers that I was mentioning before. It's actually a couple of papers, one for the upper and one for the lower bound. And it's extremely nice. Okay, so Okay, so that's what I'm going to say about entropy, that if you're talking about multiplicative, it can be done very sublinear. If you're talking about additive approximations, it's still sublinear, but n over log n, not n to the 1 over, not n to the alpha for alpha less than 1. Okay, so that's something. Compressibility of data. How to estimate the compressibility of data? In general, this is an undecidable question, but if you talk about according to a certain compression scheme, then it becomes a decidable question. Okay, so sort of you can't estimate the Kolmogorov complexity of a string, but you could hope to say how much can this string be compressed by Huffman coding, or how much could this string be compressed by Lempel-Ziv, or run length encoding. Okay, so Huffman coding is essentially estimating the entropy. We already talked about that, so I'm not going to talk about that again. Run length encoding, you can actually get some additive and multiplicative results that are sublinear. I forgot their running time, but I think it was I'm not going to say anything because I can't remember what the running times were. Lempel-Ziv turns out to be very related to the problem of support size, which we just talked about. Okay, so again, you can get weak approximation of the compressibility of the data. Weak meaning like you can distinguish compressible by root n versus not, something that cannot even be compressed by a constant factor versus something that can be compressed a lot by root n. That kind of approximation you can do in sublinear time, but distinguishing compressible by a factor of 4 versus only compressible by a factor of 2, that starts to take more time. That's more like n over log n. Okay, so that's nearly linear. All right, so there's all these examples. It really depends what you want to do and what kind of approximation. Most of these you can do in sublinear time. Some of them are kind of dramatically sublinear if what you're looking for is a weak approximation. But if you want a really good approximation, you can still get sublinear, but it's more like n over log n. All right? Okay.
What's the high-level sort of distinction between this and entropy estimation? If you know you have...
They're very similar. They're very, very similar.
What's different?
I mean, in the problem or the...
I don't know. As far as, let's say I want to estimate how well is the going to work. How many units it's going to return to the source. If I estimate the entropy, then I know that's going to be off by just a small amount. So somehow estimating entropy should be sufficient.
Okay, so maybe I should take this offline because I'm not sure...
You're somehow just saying that this is a different problem than entropy estimation, right? Or maybe I'm missing.
So I guess the question is...
Because in my head, the compressibility of the data is sort of equivalent.
So estimating the entropy means what in your case? Like
See, this is for a concrete string or something, right? Your input is a difference? Okay, you're not getting samples from distribution.
But you're sampling a string.
Problem where you just have some string and I want to say what's the output.
Yeah, it's not purely... It's like how many samples to the string do you need?
Okay.
Yeah, but that's right. So it's a...
So this is the model. It's a different model.
It's a different model. That's right. That's right.
Yeah.
That's right. Yeah. Okay. Okay, thanks. I want to mention one other model. I'm not going to say much about it, but I want to mention one other model. What if you have like a number of distributions? You have a collection of distributions, and you want to estimate properties of the collection of distributions. Okay? So here, you might want to know, like maybe each distribution comes from a sensor, and it's like spewing off numbers. Or, let me give a more concrete example. And this is a real data set. Maybe you have flight delay times based on airline. Okay, so you can there's a database out there called there's a database which runs on flight. I've been working with somebody in the database community, Additive Paramaswaran, and he, I think when he was a postdoc in Sam Madden's group at MIT, and they had this database of flight delay times, and they built this system that allowed you to get a random flight. You would give the system, say, American Airlines, and it would give you a random flight of American Airlines and tell you what the delay time was. Okay, so these are distributions where you can decide which distribution you want to query, and then you get a random sample from that distribution. Okay, so this is that's actually even different. It's not a distribution, it's a random number according to a sample. But it's, so, but somehow this is a different type of query. So you have a collection of distributions now. You can decide which collection you're taking a sample from, and you may want to know various things about the collection, like maybe you want to know if all the distributions in the collection are identical, or are they far from being identical, okay? It turns out that problem is just a way of restating the independence problem, okay? So that particular problem I just said is completely, it's another way of saying, essentially can be mapped one-to-one to the independence testing problem. Okay, so that's one thing. You might ask, can the distributions be clustered into like k groups where all the distributions in each cluster are similar? So it's sort of a clustering problem on distributions, which is a little different too. We looked at this. We only made progress in the case where k equals 1, which is kind of depressing. There's a lot of big open questions here. Here's another question you could ask. Do all these distributions have the same mean? Do they have similar means? Okay, you want to pass distributions where they all have similar means, and you want to fail distributions where you have to change them a lot to make them have similar means. Okay, it's kind of like ANOVA, but it's different in two ways. One way makes it harder, one way makes it easier. Okay, so in ANOVA, usually they assume that the distributions are normal and and that they all have the same variance. Okay, and we make no assumptions on the distribution, not that they're normal, not that they're anything. Okay, they could be like all your weights on 0 and all your weights on 1. I mean, it could be completely. So in that sense, our results are stronger, but then their results in ANOVA are stronger in the sense that they ask, do all the distributions have similar means? And we aren't asking that, we're asking sort of a weaker version of it. Is it the case that we want to pass if all the distributions have similar means, but we want to fail if they're not even close to having similar means, meaning you have to change a lot of kind of a weighted sum of the distributions. It's like I have to change epsilon fraction over all the distributions in order to make them have different means. Then I want to say fail. Okay, so it's quite a bit more of a weaker approximation than ANOVA, but it is interesting to compare to them. It's a different problem, easier in some ways, harder in some ways, but it's same kind of hopes. All right, so I just wanted to mention this model because I think there's a lot of open questions here. We talked about similar means, but what about if it has monotone increasing means? Maybe you want to ask if the means are k-flat. Maybe it comes from a sensor network and you want to know, is like the traffic getting heavier? Are we getting closer to the source of the fire? Or something like that. So you don't expect them all to have the same distributions, but you want to talk about their means. Okay, so that's just the model. Some work, but not too much work. Lots of good questions. Okay, so let me talk a little bit about testing via shape. There's a lot of distribution families that are defined sort of by their shape. Okay, so I hope you'll give me a little leeway here, but there's monotone distributions, there's t-modal distributions, they go up and down at most t times. There's Poisson binomial, they have a very specific shape. Log concave distributions have another kind of shape. And let me mention another important type of distribution defined by shape, and that is k-flat distributions. Sometimes they're referred to as k-histogram distributions. These are very these are distributions whose PDFs are very compressible because you just have to say, here are k ranges. I'm going to divide the domain into k ranges, and then I'm going to give you a weight for each range, telling you how much of the distribution is on this part of the range. And then you assume that from there on it's uniform. Okay, so this guy, everybody in the same flat gets the same weight, and their total distribution is just this area. Okay? So this is very compressible. Okay, and what we're going to talk about is how to use k-histograms to approximate other families of distributions. Okay, why do we want to do this? Well, it turns out that monotone distributions, t-modal distributions, monotone hazard rate distributions, and many other kinds of families are very well approximated by log n flat distributions. Okay, so what it gives us is sort of an so there's some family of distributions we want to test. Before we know anything about how to test that new family of distributions, one thing we might want to do is figure out how well it's approximated by k-flat distributions for some small k, and maybe we could use that in our testing algorithm. Okay? So if we know how well this, if we know that this class of distributions is well approximated by k-flat distributions for some k, then what we can do is somehow find a k-flat partition of the domain. You know, we get this new distribution. I don't want to actually, I mean, in some sense, this is kind of like learning it, but I'm not going to learn it element by element, but I'm going to see, does this work? You know, if this learning algorithm works, then maybe, okay, in some sense what I'm saying is this. If I knew it was a k-flat distribution, right, then I could try to learn the edges of the k-flat distribution, and then I could, you know, and then I could try to learn this distribution. If I knew it was, then I would say I only have to look for k breakpoints, and then maybe I'm done. Okay, but I don't know that. Maybe on each flat, it's like, it's like very far from uniform, but it kind of looks uniform. Okay, actually, I didn't give you guys the lower bound for uniformity testing, and I realize now I should have said that. I didn't give you the square root n lower bound. That's easy. So I just want to, this is a good time for me to say, since this is somewhat tutorialish, right? I just want to remind you why it's easy to see that there's a root n lower bound for uniformity testing, and it's going to count here too, okay? Because this is an important example. So consider, I need to distinguish the uniform distribution. Okay, so this is just 1 over n from this distribution. Pick a random half of the domain. Okay, so and then each of those on half of the domain, I'm going to assign them probability 2 over n. But it's completely randomly chosen, okay? So maybe this will be a whole run of elements which I pick, and so on. So each of these gets probability 2 over n. Now, I cannot distinguish this from this until I see a collision. Okay? I cannot use the names, because that doesn't help me at all. It was chosen randomly. And you can formalize this. I'm just giving you high-level ideas why. But the names don't help you at all. You see element 1, you see element 4. It doesn't help you to know that it was element 1 and element 4. The only thing that helps you is to know if you saw collisions. Okay? So, and this can be formalized. That's true for any symmetric property, and uniformity is a symmetric property. So I see these collisions. I mean, I see these elements. As far for about root n over some constant many samples, I never see a collision. Because this one is uniform over a set of size n over 2. I'm not going to see a collision until I take square root n over 2 many samples. So I don't see a collision in this case. I don't see a collision in this case. As far as I'm concerned, I'm just seeing random numbers that are distinct from each other, right? I cannot tell the difference until I see my first collision. My first collision will happen faster here than it does here. At that point, I can distinguish. But until then, it looks the same to me. Okay? So what I want to say is, if I don't know things are k-flat, then I don't know if what I have is a bunch of, like, here's 2 flat, right? It could be totally random here and random here. Like, I could have a random half the subset, kind of like that. Or I could be uniform. But if I'm promised that the thing is k-flat, then I could just learn the endpoint. If I'm promised that it's k-flat, I could just try to learn the endpoints and be fine, right? So what I'm going to do is pretend the thing is k-flat, okay? I'm going to learn the edges as if it were k-flat. And then I'm going to try to test and make sure that this is the right distribution. And I'm going to use sort of uniformity testing algorithms to do the test. Okay, so it is like learning, but it's like, but then I have to test that I really did get a good approximation. And it only needs to work when the thing really was k-flat. Yeah?
So if I have a k-flat distribution, do I just plug in k for n? Because the effective support size is k in some sense.
Yeah, so you're saying for support size n.
Complexity requirements.
Okay, but all my running times are going to be horrible in terms of k. Like, they're going to be linear in k. So it's true that.
Running times are, but the sample complexity should depend on k, like the general results depend on n. Is that right or no? Right, because I'm sort of thinking.
Oh, that's a good question. Okay, I'm going to give you upper bounds where they're. these upper bounds are not the,
Not that.
when k is really big, like linear in n, you're not going to want to do this. So, okay, good question. But you're not going to want to do it this way when k is really big. So we're thinking of k being like logarithmic. Okay, so what we're going to do is find a k-flat partition of the domain, and then we're going to estimate the weights of the k-flats, and then, this thing, if it really was monotone, then it was supposed to be log n flat, then this whole thing really would work. And now we have to check if it really was monotone. So is this thing really close to my original distribution? And that's what we're going to check at the end here, that this thing we learned is actually close to the distribution. Okay? And if it's not, then we did not learn the distribution. So notice we're not learning unless the distribution had the property. We're only learning if the distribution, okay, we're only learning if the distribution had the property. We are not learning if the distribution did not have the property. So it's not actually a learning algorithm. Okay? All right. So, monotone distributions, it's kind of that picture. We're assuming some kind of total ordering over the domain. They're kind of interesting to look at. In the beginning, when we looked at monotone distributions, people are like, why are you looking at monotone distributions? But it turns out that, monotone k-modal distributions and monotone distributions, many types of classes of distributions can be described as being broken up into various monotone parts. Okay, so that's why they're interesting. I just want to point out that monotonicity testing also takes root n samples. So I gave you the lower bound here for uniformity testing. Monotonicity testing can be reduced to uniformity testing because if you take a distribution, okay, let's say you want to see if, I want to show that monotonicity testing needs root n samples, okay? So the reason it needs root n samples is if I could do faster, I could do uniformity testing faster. Because here's how I would do uniformity testing. Let's say you give me P and you ask me, is it uniform or not? Okay? So one thing I could do is ask, well, is it monotone? And is it anti-monotone? Like I could take the reverse of I could relabel the domain elements so that they're reversed, right? So I could ask if both of these are monotone, then it must be that my original distribution is uniform, because the only way that both P and P reversed can be monotone is if, and this you can easily prove, is the only way both of them can be monotone is if actually they were uniform. Okay? So this is just a simple reduction to see that it has to be at least root n sample complexity to test monotonicity. Okay? Questions on this? P reverse, we got that, right? Okay. All right. Okay, let me just mention, we didn't know this at first, but there actually was a really nice, since I'm in Paris, I have to mention him. There was this really nice notion of Bourget bucketing, okay? So I'm told that he would be really upset if he knew that we're actually using his results for worrying about n, because he doesn't like asymptotic dependence on n. But I never met the guy. But I hope he's not here. Okay. So this is a really cool thing to show you that monotone distributions can be approximated by log n histograms. Okay, I'm not actually going to show it to you, but I'm going to show you what he said. And this has really nice properties. You can partition the domain into 1/epsilon log n buckets total, so that any monotone distribution can be approximated as a k-flat distribution according to this partition. And the cool thing is this partition is the same for every monotone distribution. Okay, so here's what we're going to do is partition the domain into segments of size 1 plus epsilon to the I. Okay, so they're going to keep getting bigger. So there's a ceiling there, but whatever. Okay, so these segments are just going to keep getting bigger and bigger, but exponentially bigger. So we only have log n partitions to get to n, right? The first ones start out having 1 element, then 2, eventually, then 3, but then, they start increasing multiplicatively by 1 plus epsilon, and you start getting out there. You only need log n buckets, and you decide this without even looking at it's completely oblivious to the distribution that you're testing. This is what's so important about these, okay? So it's both log n buckets and completely oblivious. All right, now take any distribution P that's monotone, Okay, so P has to, I left out the word monotone here, but let P hat be the distribution that's uniform on each one of these buckets, but has the same marginal in each bucket. Okay, then what you can show, Berger showed this, and there's a simplification and also a case in a paper by, I'm forgetting the 3 authors, but one of them is Daskalakis. So if you ping me, I can send you the right reference. But what you can show is that P minus, the distance between P and P hat in L1 distance is at most epsilon. Okay, where this is the, it has to do, this is the epsilon that tells you the number of buckets. So this is the Berger approximation. Okay, so one easy way to test monotonicity is take the Berger approximation of your distribution and test, is this close to your distribution? But what you're going to have to do is check that your distribution is really uniform in each of these buckets. Okay, so it's not enough to know that your distribution gives the right weight to each bucket. You actually have to know that it's like not crazy with the right weight, but it actually is uniform in each bucket. Okay, so that's why we're still going to have root n sample complexity, because we have to do all those uniformity tests. Okay. Okay, so that's what I want to say about Berger. But the generic algorithm idea is approximate the distribution by k-flat distributions. So we're going to partition the domain into k intervals, and our conditional distribution should be uniform in each. And then we should check if the k-flat distribution is close to being in the class. So in this case, we knew we would check if it's close to being monotone. In the case of monotone hazard rate, you'd have to check a different thing. But you're getting like these weights. And now you have to check if there's something in the class that you're testing, like you're testing whether this distribution has monotone hazard rate. Okay, now you somehow partition this thing into a k-flat distribution, you figured out the weights. Now you have to see, is this thing close to being in the class? Okay, what might happen in your monotone case is you might have something that looks kind of like this, where it's a little bit higher on that bucket because of sampling error. And then you might go down, and it might look something like that just because of sampling error. Right? So you just have to check, is this thing close? It's all right to have sampling error. You know, we expect that. But you have to check, is it close to being monotone? Okay? Is it close to being monotone hazard rate? Is it close to being k-modal? Whatever it is you're testing, you got to check closeness. But you have to allow a little bit of error because you will have sampling error. Okay. So this, so what are our questions? First of all, we need to prove some kind of theorem that says this class of distributions can be approximated by k-flat distributions for some small k. So there's always some theorem like that for each class. Then you have to give a general procedure for finding the interval boundaries. And then, and you can't do this assuming the distribution has the property. You have to say that the thing works even if the distribution didn't have the property, because it's a tester. The tester needs to work even if the distribution didn't have the property. Okay, and then how do you check that the k-flat distribution is close to having the class? This is a computational problem. You don't need further samples for this. But I mean, one of the usual ways we solved this one was solving some sort of linear programming, usually on something like logarithmically many variables, so it wasn't such a big deal. I mean, certainly computation wasn't the problem here, okay? So, okay. How would you find a k-flat distribution? Well, one thing you could do is recursively partition your range into half, unless, okay, so you would recursively, like you have some kind of distribution, and you see, is this k-flat? Well, okay, so this is what the algorithm is going to do. I'm going to assume that I'm looking at range I through j. I test, is the thing uniform, all right? Now, maybe the probability assigned to this range I through j was so small that I can't even do that test because I don't get samples, okay? Then it's so small, I just say forget it. I'm not testing, I'm just dropping that interval, okay? But if otherwise, I want to do a uniformity test and make sure that it's kind of looking uniform on that range. And if the collision probability is small, I say, oh, this looks uniform, I can stop. If it's not, so that's great. And that takes me root n samples. What if it says it's not small? Maybe the collision probability is really high over this range, much more than it should be over a range of this size. Then what I'm going to do is I'm going to subdivide it in half. And I'm going to recurse on each half. Okay? So, and then if I have too many partitions at some point, then I can say, oh, this is not in the class. This distribution is not in my class because my class was could be broken up into log n intervals, and I've got much more than log n intervals here. Okay, so at some point I can just stop if I'm getting too many partitions. Let's just do an example, because that was sort of high level. Here's a distribution where it's 1 over 2n on the first half of the domain and 3 over 2n on the second half of the domain. So what would we do? We'd check the collision probability on 1 through n. We start here. We see that it's high. Okay, so we subdivide it into 2. The collision probability is too high for this to be the uniform distribution on 1 through n. So we subdivide into 2. Now, my collision probability, given that I'm in the first half of the domain, is perfect. So I say, oh, uniform on this half of the domain. And my collision probability, given I'm on the second half of the domain, is also perfect. Great. So now I say, this is great. This is approximable by a k-flat distribution where 1 through n over 2 is one flat, and n over 2 through n is the other flat. Okay? So that's kind of what you want to do. You just want to break up sections that are in half that are not looking uniform. Okay, let's just to see what happens in another case. What if I have an exponentially increasing thing? You know, the biggest element is half, quarter, eighth, and so on. Okay? What would this guy do? Well, the collision probably is too big, so I'd subdivide it in half. And then what happens here? I test the collision probability here. I get no samples from here. There's nothing here, right? The total probability here is tiny. So I say, forget it. You know, I ignore it. Just ignore it. Okay? But here I'm getting a bunch of samples on this side. The collision probability is way too big. Subdivide it in half. Okay? Now, again, I subdivide in half. This side is still getting nothing. Nothing. So forget it. That's too small. Okay? Here, my collision probability is still too big. Okay? I keep going like this, log n times, until I get to my last log n elements, which actually show up. Okay? And then, you know, then I can decide whether this thing is log n flat or not. All right? So this takes this whole thing looks like a line of log n, and then down here you'd have a tree of depth log n and total size log n. So that's what would happen there. Okay. All right. So you can use this kind of methodology to look at all these classes. Batu et al. Looked at monotonicity. Canon et al. Looked at this as a general paradigm and looked at all these different things. You know, for each one you have to show that it's close to k-flat, and for each one you have to give an algorithm which allows you to estimate whether a particular k-flat distribution is close to being in the class or not. You know, other people have looked at other kind of general paradigms for constructing testers for distributions, such as Acharya et al. And all these classes have been looked at in other ways by other people, more kind of one by one. So I don't want to claim that this is the first set of papers to look at all these problems, but so I gave a bunch of other references down here. Okay. I want to say there's a lot of other questions to look at. I should mention k-wise independence has been considered. You can do much better for k-wise independence than for kind of total independence. So k-wise independence means that if you have like a vector of length n, let me use d. If you have a vector of length d and you look at k-wise independence says that any k slots in the vector look totally independent. Okay, but if you look at k plus 1, they may be completely dependent. So that's k-wise independence. You can test k-wise independence with n to the k samples, maybe it's n to the 2k, n to the order k samples, and there's a non-matching lower bound. It's kind of off by a square root factor between k-wise independence. I'm probably forgetting some recent work on this one, but something's ringing a bell that I think I'm forgetting something. But in any case, at some point, that was the results, that they were off by a square root factor. You can also look at monotonicity over general posets. You know, there's a lot of open questions here. There's some things known, some things not known. For example, monotonicity over the hypercube. There's been work specifically on k-histogram distributions. I think that sort of fits in with what I mentioned before, and lots more. Okay. So I just want to say there's kind of a lot of different properties that haven't been looked at. And I think there's really a lot of open questions. How many more minutes do I have? 10. Okay. So I'll say a few more words then. So one thing is that kind of upsets people is the dependence on n, because like cryptographers, they always want to know that their pseudo-random generator is, their random number generator is uniform. And how can you do that? For them, these results are exponential. You know, like square root of exponential is still exponential for them. So that's kind of upsetting, you know. But, you know, there's nothing to do. There's a lower bound, right? So what do you do? Well, so basically, the question is, are these results at all good or bad? You know, on one hand, we've got lower bounds. That's the best. So it is non-trivial, but it's still kind of upsetting. So what could you do if this is too much for you? All right, so I just want to say, and I'm not really going to give examples here, I just want to say there has been a lot of work done on this, lots of open questions, though. People have looked at restricted class of distributions, such as, let's not assume that the distribution is Gaussian. Let's assume it's bimodal and then test it's Gaussian, for example. Okay, that's going to be much faster. Or let's assume it's k-modal and test that it's bimodal. You know, let's make some assumption, weak, but not all the way down to like it's a Gaussian and it has the same variance as everybody else. Okay, so then there's there's a few results. I think there's a lot more to do in this case, restricting the class of distributions. There's also some surprising things. You can assume a distribution is monotone over a totally ordered set and get much better results for testing properties of uniformity, testing properties of identity, testing properties of independence. But if you assume it's monotone only over a partially ordered set, like you have a distribution over the Boolean cube, and you assume it's monotone only over the Boolean cube, like if an element dominates another element, then it should have higher probability. Okay? But now you want to test that it's uniform. Okay, that you can do in time logarithmic in the domain size. But if you want to test if this distribution is a product distribution, that requires time that's like, you know, the domain size is 2 to the n. So that was going to require 2 to the n over a constant many samples. So you would think, you know, if you can test uniformity, why can't you test product distribution? Like uniformity testing takes the dimension. Uniformity takes the dimension many samples. Why does testing product distribution take 2 to the dimension over a constant many samples? But that's life, you know. Even other than uniformity testing, everything seems to require a lot of samples. Okay, so things become kind of interesting depending on what kind of structure you assume. There's also been some really nice work on competitive closeness testing, where you sort of compete with the best algorithm. And another thing that people have done is to look at other distance measures. So, you know, people have looked at earth mover distance. People have looked at LP testing. Oh, wait, that is LP. So sorry, that's a different model. Okay, people have looked at earth mover distance in the distributions. It makes things easier, but not as much as one would hope, especially not in terms of the dimension. But maybe there are other things that one can do. Okay, and another thing that people have looked at is what happens when you have more powerful query models. And there's actually a lot of cases where this might be actually useful. Like you may, for example, sometimes have access to, I may be able to query the probability of element I, as well as get a random sample. Okay, so this is something that databases sometimes support, such as Needletail that I mentioned earlier. And also, for example, Google has the n-gram data written, like they actually calculated n-gram data over a whole set. You know, so sometimes people spend this overhead of calculating all kinds of data, which would, from this you can get the probability distribution function of any given domain element. And you can also, you know, it's a big file of things. You could just take a random sample. You know, so it should be easy to get a random sample from this data. Okay, so there has been a lot of work done on this. I'm not saying much about it, but there is a survey due to Clément Canon, and he talks about this a lot. Okay, if I have, so how much did you say now?
Whatever, 6, 7 minutes.
Okay, so 6, 7 minutes, I'm going to talk about some other thing. Okay, so I want to talk about, okay, now you've tested this distribution, and it's close to monotone, or close to bimodal. Now what do you do with it? Suppose you want to use this distribution, and you need it actually to be monotone. All right, so, you know, maybe, you know, what are we talking about? You might have errors where you just didn't receive certain data. and you have no idea what it is. You may have places where the sensors went crazy. Like essentially it's monotone distribution, but some of the sensors just went crazy, and so it looks like the traffic is increasing as you get closer to the city center, but there's some really weird bloops, and you're pretty sure that was a power failure. Okay, so that could happen. These are just some examples. Sometimes the data could be wrong because of location errors. Let's say move on because I only have 6 minutes. But now you get this, data. This is your estimation at the. If you took the time to learn your distribution, which I'm not saying you should, but suppose you did, maybe this is the distribution you would get. And now, what do you mean by correct it? Like, how are we going to correct this? So, now do you think that's a good correction of the distribution? Or is that a good correction? Who wants the first option? Shall I show you again? Guy wants the first option. So, okay, that's one option. And this is option 2. Who wants option 2? Okay, I got 5 votes for option 2. So you lose. But I'm glad I have people like you in the audience. All right, so we don't know what to do, okay? So what's correct? Well, there's a lot of work out there and what to do with wrong data, missing data, imputation, missingness, outlier detection, removal. There's a bunch of things. And a lot of it assumes somehow that the distribution started out as being normal or Gaussian, or something. There was some assumption on the data, and now we're going to fix it based on these assumptions, all right? But what if you don't have these assumptions? Okay, so, what we're going to suggest is a methodology for sample correcting which says, okay, I'm going to assume something about the distribution, but I'm going to assume something weaker. Okay, what we're going to assume is they came from a certain class, maybe not the class of Gaussian distributions, maybe the bimodal distributions. Something weaker, and then we're going to try to correct to bimodal instead of all the way to Gaussian. Okay, because we don't know, maybe it's not Gaussian. All right, so so we're going to assume the original distribution was in some class P, and the sample corrector is going to be defined with respect to that class P. So P could be monotone, Lipschitz, k-modal, whatever you pick. Okay? And what you're supposed to do is, given a distribution that you're promised is epsilon close to being in class P, what you'd like to do is output samples of a new distribution, Q prime, that is in this class P. Okay? And it, of course, that's trivial, but it should also be close to Q. Like you can always pick your favorite distribution in P and output that, but it should also be close to your original data. Okay, so Q prime is in P and also epsilon prime close to Q. So, Q is epsilon far from P. It's within epsilon of P, so I have to let this epsilon prime be a little bit bigger than epsilon, hopefully not too much bigger than epsilon. So I'd be just to give myself some leeway. Okay, so now you can ask some questions. What's the sample complexity per output sample of Q? Like when can I start outputting samples of Q prime? Do I actually have to wait until I've seen enough samples of Q that I've learned it? Or can I do something faster? And also, another side question one could ask is, what's the randomness complexity per output sample of Q prime? Like, can I, do I have to add my own randomness to the situation? Okay, so I'm going to sort of ignore this second question. But one thing to notice is that if I have an agnostic learner, then we can get a sample corrector. Okay? So if I take enough samples, what does an agnostic learner do? It learns, it can tell you, it outputs, I'm getting samples of something that's close to being in the class P. An agnostic learner says, even if it's just close to P, I can learn something in P that it's close to. Okay, so an agnostic learner is quite powerful. And if I have that thing, then I can use it. Once I've learned it, then I can output according to this thing I've learned. And that will be my Q prime. Okay, so learning, agnostically learning, which is harder than regular learning, solves this problem for me. Okay? So that's just one thing to notice. And, this gives us a bunch of corollaries. You can get sample correctors for all these problems. I don't want to go into it. But what I want to say is kind of the whole game then is really, when can we do better than agnostic learning? I think at this point, because once you have such a general statement, then you say, okay, can I do better than agnostic learning? And we know, for example, that learning monotone distributions requires omega log n samples. This was the paper I couldn't remember before. This was the simplification of the argument of Berger. And it turns out, And we don't know, actually, we don't really have a good answer to this question, I should say. But for monotone distributions, you can get certain, maybe slightly non-trivial things to say. I would say there's a lot of big open, there's a lot of open questions here, like what properties can you correct with faster than the agnostic learning bound? That's the major open question. You can say a little bit about monotonicity. If it's really, really, really close to monotone, you can obliviously correct it. If you're given extra power in terms of queries, then you can correct faster than learning. There's a few cases, but the general problem, it seems unlikely that we can do a whole lot better than agnostic learning. And I'm not going to say too much about it because I'm running out of time. I want to say these sample correctors are really useful in the sense that if you had one, not that we do, but if you did, then you could turn a learner into an agnostic learner. So, if your sample corrector takes already the amount of time as an agnostic learner, then this won't help you. But if you have a fast, it's not going to help you if your corrector is running as slow as the agnostic learner. But if your corrector is faster than the agnostic learner, and also the learner is faster than the agnostic learner, then you can kind of improve your best known running time for the agnostic learners. So that's one thing. And it also turns testers into tolerant testers. So maybe this is good news, maybe this is bad news, because maybe what this says is that it's easy to get lower bounds for these sample correctors. Not sure. Okay, if you look at special error classes, you can also get better results than what we said, such as if you assume that all these sensors are broken and not sending you samples, then maybe you could, then you can get better results. Unfortunately, these results are also based on learning who's missing, and that's sort of what I was hoping to avoid. But at that point, this is what we have. Okay, so I think that's like a really nice question: is if you have like sections that are missing, can you do better than just learning the part that's missing, like learning what's missing? That's okay. Let me ignore this slide and just say that the big open question I've already said is, can you correct faster than you can agnostically learn? What are the properties you can do this for? And what are some other applications for this thing? Okay, so basically I'm ready to conclude now. I think I'm out of time anyway, so it's just in time. I just wanted to say that basically in conclusion, there's distribution problems everywhere. For a lot of problems, we can use a lot fewer samples than might be apparent to the, might be immediately apparent. There's a lot of cool ideas out there, and I've only mentioned a small portion of them. There's a lot more cool ideas out there, and a lot of cool techniques, and a lot of great colleagues. So it'd be great if people joined and worked on this. So that's what I have to say.